compute these partial derivatives. And say again. So if I have a function of z with respect to x and y, as long as you already know how to plug in, you can also understand this chain rule from a plug-in point of view, right? So if I plug in st right here, I eliminate the variable x. If I plug in st for y, I'm eliminating the intermediate variable y. So I will have a new function of z with respect to s and t. Therefore, there should be definition of a partial derivative with respect to s and t. Okay? So the chain rule says partial z, partial s is going to be partial z, partial x, partial x, partial s, plus partial z, partial y, partial s. So the chain rule for this function is pretty similar to that one. The only difference is because all these dependencies here are partial, so everything is partial derivative, and that's all. So if I'm taking derivative with respect to z, I go x, and x will depend on s, all right? And then I will take the dependence of y will depend on s as well. So that's why I have these two components exactly as what we have over there, okay? So this is hitting on x, s hitting on s. And then hitting on y hitting on s. Because we're computing the derivative with respect to s. Okay? So as long as you have this formula, how do I set the partial z, partial t right here? Partial z, partial x, partial t, plus partial z, partial y, partial y, partial t. Okay? So these are more general formulas for the chain rule. We have two intermediate variables and two new variables, s and t. Okay? Again, I want to stress that these are all partials, and also I can freely choose my letter here. I can begin by z as a function of s and t. S and t are two functions with respect to x and y. So the letter choice here are pretty arbitrary. You can choose any letter you want, but the formula is still the same. Okay? So now I want to practice a couple of examples, and then we will see a very nice application of chain rule. Okay, so I have a function. Z is equal to e to 8x plus 2y. X is equal to 8 multiplied by st. Y is equal to 3s minus 2t. So I want to compute the partial s, partial z, partial x, and partial z, partial t. Again, for this kind of problems, you have two ways to go. Either you can plug in s and t directly into this function, and then you got a function involving s and t. You can compute the partial derivative directly for that new function, or you can use the chain rule. Because our main goal is to use the chain rule here, there are a lot of advantages for using chain rule. So that is the simplest form. You don't see the significant advantage. There are a lot of other problems where the function is not very explicit. A lot of functions are quite implicit. The chain rule has a lot of advantage on these cases. So for this problem, I just want to use chain rule to practice. Partial z, partial s. I want to find a target man, but everybody can work together. So Ellie, is Ellie here? Yep. Okay, so let's work together. Partial z, partial x, partial x, partial s, plus partial z, partial y, partial s. Okay? So we are computing the partial derivative with respect to s. Every last denominator has to be s. Right? Yeah. So what do you have? Partial z, partial x for this guy. The derivative, exactly. you have the exponential derivative is just itself. All right, so 8x plus 2y. And then I have to take the derivative of the exponent. So I get 8. All right, because I'm taking derivative with respect to x. That with me? And then partial x, partial s. 8t, exactly. So t is the constant, so I'm getting 8t. Are we all getting these partial derivatives? Yeah. Okay, so partial z, partial y, what do you have? So x becomes the constant here. So, but it's still taking derivative exponential, right? So it's going to be e to the 8x plus 2y times, y is the variable here, right? It's times 2. Then multiply by partial y, partial s. It's just partial y, partial s. T is the constant. This is like taking the derivative of the t, sorry, of y with respect to x. This is the 3, all right? It's 3. So in the end, I'm getting a 64 e to 8. I want to replace everything by t and s. So it's going to be 8 multiplied by 8st plus 2 multiplied by 3s minus 2t. These plug-ins are just a simple algebraic simplification. So we can all work this separately. So 8 multiplied by x, so it's going to be 8st minus plus 2, 3s minus 2t. So if I simplify everything with respect to s and t, I have 64 e to 64 st plus 6s minus 14 plus 6 e to 64 st plus 6s minus 14. Okay? I think I missed a t right here. Okay? T right here. So that is going to be what you have. Okay? You can similarly compute partial z, partial t as well by doing the similar computation here. The only thing is you change the s to t. Okay? So this is the simply application of this formula. Again, the number of the variables is not the issue here. You can introduce any number of variables here, and you can derive your own chain rule formula. I'm going to give you one more here. So if I have a function w is equal to f, x, y, and z. Okay, so if I have 3 intermediate variables and 2 new variables here, so z is equal to z as t. Again, you may ask, what the heck are we doing this? This formula will come back again when we introduce spherical coordinates and the cylindrical coordinates. Okay, I want to mention it here. For instance, in the 3-dimensional space, the general choice of variables will be x, y, and z. But there are other ways to categorize points in a 3-dimensional space. There are cylindrical coordinate system and spherical coordinate system, which are widely used in daily life in any scientific research here. So then you have x, y, z as your x, y, z coordinate system. And then this st or rho will be the new spherical coordinate system and cylindrical coordinate system. In order to see the relation between these coordinate systems, we have to compute these partial derivatives. Okay, so this is a very important chain rule, and it will come into play once again, maybe 1 month later. So when I have one more variable here, so I can make a corresponding modifications here. Okay, so I want to compute the partial w, partial s, and the partial w, partial t. So for the partial w, partial s, I have partial w, partial x, partial s, partial w, partial y, and partial y, partial s, plus partial w, partial z, then partial z, partial s. I'm still doing the derivative with respect to s. All right? And then, if I'm taking the derivative with respect to t, So you can derive your own. It's going to be partial w, partial x, partial t, partial w, partial y, partial t, and add by partial w, partial z, partial x, and partial t. Okay? So if you have 3 intermediate variables, and every stage you have to hit each one of them, and then each one of them will give you another partial derivative with respect to the variable on the compute. Okay? So if you have 3 intermediate variables, 2 new variables, you're going to have 6 different combinations for computing these things. All right? If, say, I have 3 intermediate variables, I also have 3 new variables. You can have 3 partial derivatives with respect to new variable here. And then these combinations will give you 9 different combinations. Are you with me? I can simply add by another variable saying I have s, t, and a t. So 3 new variables. So I can eliminate x, y, z to get a new variable, a new function with respect to that. Again, for all the partial derivatives involving chain rule, there are always 2 ways to go. You can either plug in the very beginning, or you can do the chain rule multiplication. Okay? Chain rule multiplication in each stage is a multiplication individually for the intermediate variables here. Now with me? So now, as long as you already get the whole idea here, I can give you a function f x1, x2, xn. I can give you n intermediate variables. Each one of them is equal to a new variable y1, yn. So xn is equal to xn, y1 up to yn. Okay? So I want to have a very general form so you don't have to be very restrictive on the chain rule here. So I can have any number of intermediate variables, any number of new variables. By eliminating the intermediate variables, I can have a very, very general formula here. So I'm not going to write down the whole formula here. So let's say this is z. So z is my dependent variable. Originally, I have a 1 to n variable here. And each one of these x variables will be a function of new variables y1 to yn. For instance, if I want to compute the partial z, partial y1, how should we go? I will have to hit on every single intermediate variable. Am I right? For every intermediate variable x1 to xn, I have to use these functions to get the dependence on y1. Am I right? So this is going to be partial z, partial x1 divided by partial y1. Am I right? Every time, this intermediate variable will change, but these two are going to be fixed according to what you want to compute at the very beginning. Plus partial z, partial x2, partial x2, partial y1. Plus you have to add on all the intermediate variables ending at partial z, partial xn, partial y1. Okay? As long as you fix y1 and z in the very beginning, intermediate variables will be all considered here. Okay, these two are all fixed. And then you can simply compute partial z, partial y2 equals whatsoever. Okay? You need to consider all the intermediate variables similar as here, and then add them together. Okay? Right now, I can throw you any function with any number of intermediate variables and new variables. You should be able to use the chain rule to compute that. Okay? So next, I want to give you a very nice application of chain rule. One application of chain rule, as I mentioned, is to transform between the coordinate systems. So if I have an x, y, z rectangular coordinate system, and now I have a spherical coordinate system, I have to find the relations between these different coordinate systems. So this chain rule will be very useful over there. The other big application is so-called implicit differentiation here. Okay? Implicit differentiation here. What the idea is, if you have a function f of x, so if I have a function y equals f of x, for instance, I can have a trigonometric function, I have a polynomial, rational, exponential, logarithm, any function here. as long as I have a formula, I should be able to use the rules to compute the dy dx. All right? I can always compute the dy over dx by using the differential rules, the product rule, the quotient rule, the chain rule, whatever. However, in the real life, a lot of the relations between x and y is not explicit. This is going to be an explicit formula. For instance, I give you this simple example. So I have a function sine xy plus pi y squared minus x is equal to 0. Okay? So in this function, as long as I write it down, are you convinced there is a relation between x and y? There has to be a relation between x and y, am I right? In other words, if I make x to change, y has to change in order to make this equation true. Are you with me? But how these two are related in the explicit form is not that clear. For instance, I can ask you to solve y with respect to x. I can ask you to solve y is equal to a formula of x. If you have a quadratic equation, you know the quadratic formula. If you have some easy functions, you can solve for y. But for a lot of other functions, you're not able to solve for y explicitly, or it is just too complicated. For instance, for this guy, it is too complicated to solve for y. It is not a quadratic equation. All right? You have a sine function right here. However, I can still compute the derivative with respect to x, okay, without even computing the explicit formula here. So this is so-called an implicit relation. So we don't have to compute the explicit formula to connect x to y in order to compute the derivative. So here is the formula. If I have a function, capital F fy equals to 0, okay? So this is a capital function f. For instance, in this particular example, my capital F will be sine xy plus pi y squared minus x, okay? Generally, if you have a function to govern x and y, you don't know the explicit relation between x and y, but you know there is. Okay, there is a relation between x and y. When x is changing, in order to make this equation to be valid, you have to make a y to be changed as well, right? So what is the function essentially? What is the function I asked you in the very beginning? Function is a mathematical description of